Welcome to the course on modern digital communication techniques, and as you are well prepared now that we have discussed receivers, that means we have seen the signal transmitted through the channel, received and processed, and finally a decision has been made. So now it is important that we try to analyze the performance of the system that we have created. So what we are going to discuss is the probability of error for some popular digital modulation schemes. So we have already identified that why do we want to call it an error, and just to summarize that since the detector chooses from one of the possible sets, that means in a very layman's term we can think of as if there are 4 colored balls and some colored ball has been received from the other side. The detector has to make a choice between which of the possible colored balls it could have been. So that means it will finally make a choice. So if it makes a choice, the choice can either be right or it can be wrong. So therefore we want to calculate on an average what is the chance it makes the right decision or what is the chance that it makes a wrong decision. And we had designed a system so that the percentage of time or the chance that it makes an error is as low as possible. So therefore we get into the study of probability of error, and what we are going to look at is some popular digital modulation schemes. The reason is there are so many different digital modulation schemes and we have studied quite a few. It may not be possible to look at all possible modulation schemes. So we will take a few which are very important and which will serve as baseline, and then you can develop based on whatever we discuss here. So first we take a look at the binary modulation scheme. So first we take a look at the binary modulation scheme, and what we have is a PAM, a binary PAM signal, where we have the signals S1t and S2t, and S1t is g of t while S2t is minus gt. So this is well known, where gt is the arbitrary pulse shape. So we are not talking about a particular pulse shape, and of course whatever we have here is non-zero for the interval 0 to t. So let the energy of gt be g cap Eg. So these notations we have been using throughout, nothing much new for you. So the signal space diagram is as over here. So again this is standard notation what we have been using, and we will assume equally likely signals S1 and S2. So what we have is the output of the matched filter for S1 being sent. So we must be careful that we are talking about S1 out of S1 and S2. So in that case the received signal would be S1 plus noise, and S1 being root EB, we have root over EB, and of course noise is described as 0 mean and the variance as n naught by 2. So now we have to go to the decision rule, and we have studied the decision rule where p is equal to half. So that means we are taking the maximum likelihood receiver because equiprobable, and for such a situation you may remember we got the result that the received vector is to be compared with 0. If it is greater than 0 it is S1, if it is less than 0 it is S2. So in other words, when I have this particular signal space, 0 is the threshold point and anything on this side will be decoded as S1, anything on this side will be decoded as S2. So now since we have sent the signal R, or we have received the signal R, we have the signal space on this axis, and we would like to draw the conditional PDF of R given S1, because that is how we made the receiver. So the conditional PDF of R given S1 would be the Gaussian PDF with a mean of S1, that is root EB, and the variance of n naught by 2, that is the variance of noise. If S2 would have been sent, your PDF would have been Gaussian with mean at minus root EB, that is the signal value of S, and sigma of n naught by 2. So, that is how you have P of r given S I being 1 or 2 denoted by this expression, which is well known to us. So, now given S1 was transmitted, the probability of error, that means if S1 is transmitted, we were trying to find that the decision is a wrong decision, is the probability that the received vector r is not on this side, but on this side. So, when I am talking about probability of error, what I mean is, suppose we have received several r values, that means I have received r, let us say 1000 times, and what percentage of time, suppose all the 1000 times I have sent S1, and every time I send S1, so that means if this is S1 I have sent it, first time I receive r is here, second time it is here, third time it is here, next time it could be here, it could be here, it could go there. So, the mean is here, but it will be scattered around this, and it could go there. So, it would go everywhere, right. So, whenever it goes on the negative side, if this is 0, we will identify it as S2. So, identifying it as S2 is error when I know that S1 has been sent. So, we are trying to calculate what fraction of time is it on the region of S2. So, that is what we have. We want to calculate the probability that r is less than 0. So, that is probability of error conditioned on S1, that means we are saying S1 is sent, is integrate from minus infinity to 0, because we would like to find this part. So, this PDF goes like this. So, if we have to make it a bigger picture like this, suppose. So, we want to find the area under this curve. If this is the PDF, the probability is equal to the area under the curve, under this curve covering this range of values, right. So, the range of value is from 0 to minus infinity, or rather minus infinity to 0 in this, for this PDF, right, that is a standard thing. So, we have minus infinity to 0, the conditional PDF, and over r dr, because r is the received vector in case it is one dimensional over here. So, P of r given S1 we directly use over here, right, and then we proceed further. With the expression that we have here is, we make a substitution that r minus root EB over root n naught is x by root 2, or in other words, we want to replace this part in the new in the integrator to e to the power of minus x squared. So, that we get a well known expression in terms of e to the power of minus x squared, and our evaluation turns out to be easier. So, now if we let r, if we make this substitution, so dr equals to dx and some scaling factor, for r equals to minus infinity, x is equal to minus infinity, r equals to 0, x has a particular change. So, you can do all these changes easily. So, this integration limits change, the integration limits that you see over here gets changed to minus infinity to this number, and you have the expression looking like this. So, moving further on this, since there is negative sign on both of them, you could swap the limits and you get an expression which appears here, and this expression can be substituted with the q function with the argument of this term, where q of x is 1 over root pi integrate from x to infinity e to the power of minus t squared by 2. So, this is a standard function and which you can only find values by numerical evaluation. So, we use it in terms of q function because this looks a bit cumbersome. So, from now onwards we will be using mostly q functions to represent the error probabilities. So, in summary, we have started off with the binary PAM. For the binary PAM, we have considered equiprobable transmission. For equiprobable transmission, we have calculated the conditional PDF of a given signal for the received vector, the received signal, and then if I know S1 was sent, the probability that it is detected as S2 is the area under the curve in the region of S2, because as we said, if there is a PDF function and you want to find the probability that the random variable lies in a certain interval x1 and x2, all you have to do is to find the area under the curve of the PDF of x in the interval x1 to x2, and this is going to give you probability that x lies between x1 and x2. Right, that is the standard thing. So, now since we want to find the probability that it lies in this range, we have to integrate the PDF in this range, and that is what we have done. That is what we have done over here. So, when we do that integration, we do some change of variables, and what we end up with is an expression of the Q function, where the Q function is described in this way. So, now the Q function is something which is not very intuitive, and you cannot make much out of this. So, there are some approximations of Q functions which are sometimes very useful, which we will refer to. So, now proceeding from this point, what we have calculated is P of error given S1. Now, what will be the probability of error given S2? That means, we consider S1 was sent and we find the area under the curve over here. So, now if we say that S2 is sent, what is the probability of error? We have to first see the PDF of received signal given S2, which will be like this. If this is x and this is P of x, because the mean is that of S2 root EB, and it has a sigma of n naught by 2. So, it will be detected as S2 as long as noise does not push it on the right hand side, if this is 0. So, whenever it goes to the right hand side, it is in error. So, if this is the PDF curve, then we want to find the probability that the received vector lies in the range 0 to infinity. So, that will be integration of this part of the curve. Because of symmetricity, this area is equal to this area, right, symmetricity because of equal probability, and it is centered around 0, equidistance from 0, and this PDF curve is also symmetric, and we also have equiprobable. So, what we have is the probability of error given S2 is what we just described. Probability that received vector is greater than 0 given S2 is the same Q function that you are going to end up with. And since probability of sending S1 is equal to probability of sending S2 is equal to half, probability of bit error is equal to probability of sending S1 multiplied by probability of error given S1 plus probability of sending S2 multiplied by probability of error given S2. Together, P of S1 is half, P of S2 is half, P of E given S1 is same as P of E given S2. So, therefore, PB is already equal to P of E given S1, which is Q function root over 2 EB by n naught, right. And since you know that D12, that means the distance between the first signal and the second signal is 2 root AB, that is very straightforward, that is 2 root AB, that is very straightforward. So, you have D12 squared is equal to 4 times EB, or EB is equal to D12 squared upon 4. So, you can replace EB by D12 squared by 4, you are going to get D12 squared by 2 n naught. Now, this is also important because the probability of error is dominated by the minimum distance among the constellation. So, I will briefly tell you that if you have a mean here and you have constellations there. So, this is a symmetric case, not much of a problem, but suppose I have constellations so my error probability will be dominated by this region compared to this region, because if I have sent a constellation point here, there is high chance of it going into error because this region is narrow, right. Whereas, if I send a symbol over here, there is less chance of it going into error, because the PDF goes like this, the PDF goes like this. If you look at the area under the curve, it is much more compared to the area under the curve over here, right. So, and things will be clearer again. Suppose I have a probability of error which is 10 to the power of -2, and I have for this case probability of error 10 to the power of -4. So, when I am taking the average probability of error, I have to, if they are equiprobable, I have to add this and this and divide by 2. If there are, let us say 2, in that case you are clearly finding that this is much more, having a much more weight compared to this, and hence the probability of error will be dominated by the high probability of error terms, which is due to the minimum distance between the constellation point. This is a bit qualitative analysis, but of course, things can be made more clearer. So, for this reason it is important to also write the probability of error expression in terms of distance between the constellation points. So, now as we said earlier, we will be using the expansion of Q function. So, as we use the expansion of Q function, we consider the Chernoff bound. So, in using the Chernoff bound, you have the limit that Q of x is upper bounded by e to the power of minus x squared by 2. So, this is not a very tight upper bound, but you can use this approximation. So, P b, which is equal to that of Q function of root 2 E b by n naught, can be said P b is less than or equal to e to the power of square of this, which is 2 E b by n naught divided by 2. So, it is minus E b by n naught. So, you have 2 E b by n naught upon 2. So, which is minus E b by n naught. So far we have this expression, and what might be of interest to you at a certain point is how does this particular function look like. So, what you can do is you can actually take log of this. So, instead of plotting e to the power of minus E b by n naught, sometimes we are interested in E b by n naught given in dB scale. So, E b by n naught when given in dB scale is calculated as 10 log base 10 E b by n naught, that is whatever we have over here. And what we can see, at least from here directly, there the probability of error decreases exponentially with E b by n naught in AWGN channel for binary pulse amplitude modulation or BPSK. So, if you were to plot E b by n naught, if you were to plot E b by n naught in dB scale, the figure that you might get in terms of error probability would look something like this, where this axis we have SNR per bit. So, here I would make a small change, and I would like to suggest that okay, let's go for binary PAM and then we will discuss this. So, what we can clearly see over here is that it falls exponentially. So, if you would have had a linear scale and this axis was in case of, sorry, if we have a dB scale over here and this axis is in terms of log, that means 10 to the power of minus 1, 10 to the power of minus 2, minus 3 and so on, you are going to get a curve which looks like this. We will see more of this very soon. So, now we next move into the probability of error for M-ary PAM signals. So, when you have M-ary PAM signals are one dimensional, that we clearly know, and Sm, the modulating signal, is root Eg upon 2 Am, where Eg is the energy of the pulse shape and Am is 2 m minus 1 minus capital M into d, and these we have covered before, and the minimum distance is d times root over 2 Eg. These things also we have considered earlier. Now, if we consider equiprobable transmission, in that case the average energy of the received signal can be calculated as 1 upon m, this is because of equiprobable. Em is the energy of the mth signal, which is equal to d squared Eg by 2 m. Now, this is straightforward from here, you can calculate this from Am, and you have this expression which can be reduced to, I mean you can do, it is an algebraic reduction from which you can get this expression where capital M is the size of the constellation. So, now when you are building the decoder, the decision rule that we have at this point is to compare the received signal R with m minus 1 thresholds placed at the midpoint. So, what we see over here is S I to S I plus 5 are the signal points, whereas tau I plus 1 are the threshold points. So, clearly what you can see is, if I have 1, 2, 3, 4 constellation points, we have one threshold between first and second constellation point, the second threshold between second and third threshold between third and fourth. So, that means, if there are 4 constellation points, I have received some vector, I will compare with these thresholds. So, just to explain that briefly, suppose this is 0, this is d, this is 3 d, this is minus d, this is minus 3 d. So, if d is sent, I am going to receive d plus noise. Noise, if it is positive noise, the received vector goes there. So, if I have sent this, if it is negative noise, this will go on this side. So, now the received vector could be anywhere in any location. So, how does the receiver work? The receiver should work in a way that if it is maximum likelihood receiver and all the points are equiprobable, we can extend our result from what we have seen before, is the decision point will be midway between the 2 constellation points, right. So, whenever I have received a signal, I will try to find that which is the nearest constellation by the minimum distance criteria, and it could be reduced to compare it with the threshold and find the region in which the received vector lies. So, if the received vector lies in this region, I would decide that most likely transmitted signal is the constellation point minus d, without assuring what actually has got transmitted. So, if d was transmitted and noise has shifted it here, I would decide it as minus d. If d was transmitted and noise has shifted it here, I will decide it as d. I will decide still at d. If it is received over here, that means huge amount of noise has been added, I will decide it as 3d, and if huge negative noise is added and it goes there, I will decode it as minus 3d. So, that means all these cases are of course errors, but what I am simply doing is comparing with the threshold which lies midway, right. So, that is what is mentioned over here. So, if there are m levels, there are m minus 1 thresholds. That is what we have, and if this distance is d root over 2 E g, half the distance is d root over E g by 2. Simply you divide this by 2 and you are going to get this particular number. So, if S m is a signal that is transmitted, the received signal is of course S m plus noise, and S m as we have seen is root E g by 2 times A m. So, therefore, the received vector is this. So, this is the constellation point and n is the noise. So, because of noise, the received signal could be in this fashion anywhere. The moment it crosses this threshold, it will be decoded as the next constellation, which is an error. If it crosses this threshold, it will be decoded as this constellation, which is an error. If the perturbed signal lies in this range, it will be detected as the correct signal. So, now to decide the error probability, we need to look at the conditional PDF. So, if d was sent, the conditional PDF would be like this, and if minus d was sent, the conditional PDF would go like this, right, and so on and so forth. So, now for this the conditional PDF goes like this. So, D, the error probability given D has been transmitted is area under this curve going up to infinity, area under this curve going up to infinity, right, and the area under this curve is same as area under this curve. So, we can say 2 times area under this curve. For minus D, it is also the same story. So, area under this curve plus area under this curve till infinity. Whereas, for these constellation points 3D, there is only one side that we see over here. For minus 3D, it is also one side, right. So, what you have is one partial PDF, one conditional PDF tail, 2 times of that, 1 and 2. So, that makes one complete conditional PDF. This is another complete conditional PDF. This has one side over here, one side over here. So, together if we consider, we have another PDF with 2 tails. So, therefore, you basically have M minus 1, because there are 1, 2, 3, 4 such conditional PDFs, but from which you have 2 PDFs which you are going to take on both the sides and 2 PDFs which will take on one side. So, you have 3 PDFs for which you are going to take on both the tails. Therefore, you have M minus 1 or 3 number of PDFs to be considered, 3 number of tails to be considered. So, to calculate probability of error, you have M minus 1 upon M probability that the distance of received from SM is greater than the half the distance, that is half the distance. That means, this R minus SM, if you look at this R minus SM is noise. So, the probability that noise has an amplitude which is greater than d root Eg by 2. So, if noise has an amplitude which is more than this or more than this, there is an error. So, therefore, you have taken the modulus sign indicated on both the directions, for which you have a 2, and this is the PDF of 0 mean white Gaussian noise, and M minus 1 upon M is what we have just now explained, that there are M minus 1 double sided tails that have to be considered. So, and the integration limit is of course, if you take one of the tails, let us take one of the tails. So, that means, this is the distance which is root Eg by 2 times d. So, up till infinity, and this is the result. So, this again you can identify it as the Q function of this particular expression. So, what you have is end result is 2 times M minus 1 into Q of this expression. Now, again evaluating with respect to the average signal energy which we have calculated here. So, d squared Eg, that is what we have like this. So, you can calculate the in terms of average energy, which looks like this, right. The average energy, if you convert d squared Eg from this expression to the average energy, you are going to get an expression which looks like this. So, you have this d squared Eg and you have EAV. So, you have d squared Eg equals to 6 multiplied by. So, from this you have d squared Eg equals to 6 EAV upon m squared minus 1. So, that is what you have, d squared Eg is equal to 6 EAV upon m squared minus 1, and that n naught is of course there, and EAV upon n naught is SNR. Now, since k is log base 2 of m, right. So, we can write that EB, average bit energy, is equal to average symbol energy upon k, or you could write EAV equals to k times EB AV, right. You could say that, right. So, in that case, if I have to write in terms of average bit energy, you are going to have, you have to multiply log base 2 of m, which is nothing but the k, and then you have EB by n naught. You have EB by n naught. So, you would like to find the probability of error in terms of EB by n naught, or as a function of EB by n naught. This is an important note over here, that for analyzing digital communication systems, we would prefer to take the x axis as EB by n naught and not signal to noise ratio, which makes the comparison different from analog communications. So, we stop this particular lecture here and we continue further with the performance analysis in the next lecture. Thank you.